Um, it's a pleasure to be here. It's a beautiful meeting and continue. Discussion that started in the morning. So what I'm going to talk is application of spectroscopy to the long-standing QRS problem. I just want to tell that I'm essentially a newcomer in this heavy fermion field. Brian has been here from the beginning, 30+ years. John Weidosh met me at some conference about 3-4 years ago, and he asked me if spectroscopy can identify the broken symmetry. And at that point I had absolutely no answer. I said that if we see characteristic electronic mode, we can apply good theoretical analysis. I didn't know that such mode exists, and we were very lucky. Sean presented the results in his results in previous talks. So we did observe. Sean actually insisted that there is a mode there. I didn't believe initially. He pushed the spectroscopy below up to 2 wave numbers to show that at very low frequencies there is a very nice strong collective mode. The mode is exactly the same as has been seen by neutrons, and then we could apply the analysis. And I think the message that Sean left us before the break was that no matter what the mode is, when the system enters in the hidden order state, the reflection symmetries must be broken. So those are the broken symmetries in the hidden order state. And the spectroscopy, the data cannot be explained in any other way, at least as far as I can tell. This is very, very important and very strong state. Since that, we collaborated with Brian's group, and we got these beautiful iron doped samples, which Brian discussed in the first talk, and we were able to apply similar analysis when the system was moved from the hidden order into large moment antiferromagnetic state. So I will mainly talk about this connection between these two states. So the work is done in the collaboration with people at Los Alamos, Ryan Baumach, who is now in Florida, and Eric Bauer, people in Brian Maple's group, and then Sean was the leading author on these two papers. So the most recent paper is presented at ARPANET. I don't need to repeat what was said in first two talks, but there is this list of very interesting properties, and I will mainly emphasize the connection between hidden order and antiferromagnetic phase. Those are very similar brothers. This has a moment, this does not have a moment. It looks like the superconductivity appears only out of this hidden order state. So if that's true, then when system is cooled from paramagnetic state, this broken symmetry that happens in hidden order state is required to get to the superconductivity, likely with broken time reversal symmetry. The spectroscopy study goes very far back. So this paper is 88. Doug Bourne, he was a postdoc with Tom Timos. And then they published a parallel where they said that this hidden order must be some kind of density wave. They said spin density wave. They didn't know that. At that point, it was unknown that there's no moment. So there's no local moment, but it resembles definitely a density wave character. So this is an abstract. They say it's essentially like this is the gap that was discussed this morning. Now, this is Brockholm's thesis work, goes back also 30 years, and already then he drew this dispersion of a collective mode. So there is a commensurate vector at 1, 0, 0. There is an excitation which is exactly the same energy as Sean showed now in Raman data. So we do know that the symmetry of that excitation, which neutrons couldn't say, even they already knew that it transforms at JZ. They see it in longitudinal non-spin flip channel. But entirely consistent now with the Raman work, which mainly couples to orbitals, we know that this excitation has an orbital A to G symmetry. And this 1,000 papers that Brian referred to in the beginning cannot be listed, of course, but the trouble was that there was no probe that could couple to excitations of A to G symmetry. I will repeat emphasizing this. Namely, A to G is antisymmetric on the XY exchange excitation. So you can't build a density matrix that would exist and therefore coupled. So most probes couple to charge density or spin density. And all those many probes will not really see the broken symmetry. So the name hidden order is a very appropriate name in that sense. All these probes are blind. This is the recent work from Kapitulnik's group, Stanford work, where they claim that in the superconducting state, time reversal is broken. I think it's a very important paper. And they also say that in the hidden order, time reversal is not broken. However, application of magnetic field, the system can be trained. So if it's field cooled at high field, then they see a Kerr effect. And heating it up can erase that Kerr effect. However, interestingly, the temperature that it's erased is above the hidden order temperature. So you need to go beyond. So that clearly suggests that there is some metastable physics beyond the mean field physics that requires, that can be induced by field cooling. I don't need to show this transparency again. I go very briefly, I repeat what Sean said in the context of crystal field theory, and I emphasize that what I'm going to talk about does not require local picture, does not require the electrons be in 5f squared, but it's a useful exercise to look in. So if we take Howley-Kotliar paper, then they will arrange the 7 states in this order. So the discussion before was what could be the different order. Those splittings are all small relative to electron volts that DFT is sensitive with, right? But the result of that Raman study that Sean presented was that these two states or other two states connected by A to G matrix elements have to be mixed, and that D4H group has to be reduced to below the hidden order transition to C4H group, and absolutely consequence of that is that there's going to be chiral symmetry broken, and then we can build a state which would be a chiral density based state, which will be consistent with hidden order. The experiment is Raman scattering, again, that was introduced in the previous talk. I repeat the transparency from the paper of 87, where then on Brian's sample, Lance Cooper, who was then a student at Urbana with Miles Klein, did these measurements, and already then they identified that in paramagnetic space, the fluctuations are in A to G channel, right? And this is this more fine work that both we were down in New Jersey and also in Paris, essentially showing that there is a strong, this is a semi-log plot, Raman response function versus Raman shift. There is a strong signal only in A to G channel. Other channels really don't have much except phonons. And if one does the analysis on that signal and calculate the real part of the Raman response function, just doing the Kramer's chronic, then these data points which are red surprisingly lie the same way on this well-known magnetic susceptibility data that Brian showed from Palstra's work of 85. So clearly indicating that the behavior of this Raman response, the static Raman response, follows the J sub Z operator response, very similar. So then there's a question of interpretation of this curve, and commonly people talk about fluctuations build up and then there is a cutoff, but I want to cut off due to Conda effects or hybridization effects. But what I want to emphasize here is that both the static magnetic susceptibility and Raman acute zero probe and the ordered state is clearly staggered state. It's a staggered phase. So in my opinion, what happens here, there's a beautiful Curie-wise temperature dependent set at high temperatures, and this is where the system locally fluctuates and doesn't really establish staggered order yet. But at this turn up in 1 over chi or turn down in chi place, it actually starts building correlation lengths at 100. That's where the neutrons see the collective mode, and that's where the hidden order Bragg peak has to appear. So this Bragg peak has not been accepted. And that's again the issue of doing the experiment the right way, because it's not magnetic and neutrons can't see that. But this is the fluctuations towards the Bragg peak, and this is where the system decides that it's actually a staggered order, not a uniform order that is being building up. So this is a quick repeat of that very nice and very difficult experiment that Sean did and discussed, which to my taste definitely says that we need to remove these operators and reduce this symmetry from here to here. So that really doesn't depend whether this is a crystal field physics or itinerant physics. This chirality, it has to be broken, and in the hidden order state, the order parameter is a chirality density wave, which is, I want to emphasize now, that the density, the charge density on this layered sides remain the same. There is no spin, there is no moment. So this is a density wave of chirality. So because there is no except this clear density distribution on hexadecapole level, if the probe is macroscopic and probing just the charge density, it's going to be silent and not detectable by that probe. Alright, so now I want to move on to the right of the phase diagram and follow the introduction that Brian already did. and discuss what happens to this observable that we can do with Raman if we go towards antiferromagnetic state. And because applying the uniform pressure is very, very difficult, so we are grateful to be able to use these samples from Brian's group, which by comparison that Brian showed, basically resemble the same phase diagram, so the iron concentration from left to the right and pressure just take us from hidden order state to antiferromagnetic state, essentially the same way, and this is still unpublished work, I believe, by Rand and San Diego group, and we have this picture in a recent shown submission on arXiv. So the picture here is the following. So this is this chiral density wave and the distribution of the functions that we expect in most naive local crystal field picture. That would be the mixture of gamma 1 and gamma 2 that allows us two ways to mix it. If we include hybridization with conduction bands and the other things, and the inherency, this picture is going to be complicated, could be way more complicated, but the main message should remain. Now, this is the magnetically ordered state, the antiferromagnetic state. And what I'm going to argue that the magnetism is an orbital magnetism. It's very similar to one that was introduced by Yoshitakura in other systems, and it turns out that we get the moment just by mixing these two states with purely imaginary operator. So if you mix them with real operator, we break the chirality. If you mix with pure imaginary operator, notice that the charge density is not broken, so this wave function remains full symmetric, but it acquires in moment. And this was actually first suggested in Howler-Kortler's less known EPL paper of 2010. They basically said that there is a continuous transformation or adiabatic continuity. This is John Milosh's term between these two phases. So basically this order parameter transforms like J sub z, and this order parameter they proposed is a hexadecapole. So this is the real part, this is the imaginary part of A to G operator. And this is the first A to G operator that you can, lowest order that you can build if you keep everything real. So it would be the fourth power, it will have 8 nodes. Then we have these two competing orders, and we can do quite conventional Ginsburg-Landau. And we can present the free energy on the plot of hidden order versus antiferromagnetic order parameter, and we can tune the system from having lowest state hidden order and failed state, excited failed state antiferromagnet, or vice versa. So in this case, strain or pressure could be the tuning parameter, and it allows to drive the system through the first order phase transition, because there is a local barrier there from one system to another. So we did experiment, the one that Sean discussed before break, on the systems as a function of error doping. And this is data very similar to what Sean showed, except this is now done on samples from Brian's group, and the previous was done on the samples from Eric Bauer's group, which had a triple R about 700. Triple R here is not that fantastic, but it still gives a very nice collective mode, clearly beyond noise. There's not much else in A to G channel. And then, if we increase the iron concentration, then this is what happens. So this mode goes to the lower frequency, it disappears for us, it's beyond our ability to see, and then when we enter in the antiferromagnetic state, it reappears in the same symmetry channel, and here's the mode. Rudy had a question about what happens with the impurity scattering. You can see that the mode is clearly very inhomogeneously broadened, so those are very high concentrations of iron. Obviously, it's hard to expect the same quality spectroscopy as we have in the clean material, so there is continuous broadening of the mode as function of doping, but it's there, and it's uniquely again in this A to G symmetry channel. So this is the spectroscopic data as function of iron doping and the energy of that mode, what happens. So how to explain that? So if you go beyond this very naive picture, where we say that this excitation is just a very naive and local picture, the excitation is between the crystal field, local crystal field. You know, on the left case, it would be transition between A2G and A1G. Then in that local picture, I would say that when I apply pressure, the splitting gets reduced, then they change, and my A1G becomes the ground state. So no broken symmetry is required to go in the magnetic state, except that the mixing will now, imagine the mixing will reduce the moment, but there is no broken symmetry in terms of space group. On the other hand, in many-body language, if I treat this as many-body ground states, I can say that this is my excitation from my ground state condensate into failed order parameter. So this order parameter is quite nearby. By applying pressure, they get closer and closer together. And this mode is essentially very similar to what Bardazis and Schrieffer discussed for the superconductors. Over there they said that, well, we have S-wave ground state, and there is a, how much?
7 minutes including question time.
Okay, I'll do that. Yeah, so S-wave ground state, and there is a D-wave, there is a interaction in D-wave channel, then the D-wave failed D-wave order parameter will appear in the spectra in the gap as a collective mode. So here the hidden order ground state, and this is essentially appearance of antiferromagnetism, which is metastable and can be spectroscopically excited or excited by any other means. This is where the states degenerate, go through the first order phase transition, and this is the opposite situation. So basically, this is the result of this discussion. The mode entirely coincides with the phase diagram, which was derived from the transport data, and the conclusions are here. So what we conclude from this spectroscopic study is that the pure hidden order state is essentially chiral density wave, no modulation of charge. There is a slight modulation of charge distribution due to the rotation of that chirality. And it's really accessible only by optics type spectroscopies. The true order parameter is staggered, and therefore one has to look for the Bragg peak. So seeing that Bragg peak would be the complete victory, not just seeing the collective mode. The companion is this, where the charge distribution is full symmetry, but the moment is induced, and this is orbital magnetism. It's a staggered orbital magnetism, and therefore this can be accessed by neutron scattering. Well, that's also basically it.
Talk is open for questions.
Just one point to clarify. So the fact that the Japanese groups have seen less than 4-fold symmetry, you would consider it as a byproduct?
Okay, so, well, first of all, there is a controversy in that field, right? So the X-ray experiment, I don't think is settled. The experiment by Stanford group, Jan Fischer, right? He clearly says that it's not a primary order parameter, and the A to G order parameter cannot couple to B1G or B2G flotation in first order, but can in the second order. So A to G plus B1G, times B1G times B2G is a allowed term in Ginsburg-Langlois expansion. And that's entirely consistent with the conclusion of Jan Fischer et al. Right? Now, Matsuda's third experiment, well, technically has not been reproduced, A, and B is done in the presence of relatively high magnetic field. So what we know then, when we apply several Tesla field, that moves the singlets around and does various things. So technically, application of that field is not a perturbative probe. It breaks the symmetry by applying the field. There's still a question why this application of field along X and Y is different. But again, in the high order, it can couple, and that would be okay. But I don't think there's an evidence for spontaneous broken C4 symmetry. Now, we know that the samples as shown are in general cracked in terms that when you cleave them and look at the Mimarsky microscope, you see rainbows. Finding a place, a tiny place, 50-50 by microns, where optically we didn't see strain field, took months and months work of Sean together with Eric Bowers for forth and back. They had many samples. So that wasn't the first cleave that this work was done. So, of course, as soon as the strain is applied, C4 is broken. Well, that's basically, okay, the last comment I have, Sean flashed, I can find the same transparency, where he is measuring on this very nice piece of the crystal, the B1G phonon, and does not see Wiesenhour sensitivity, which is fantastic, leakage of that mode in any other forbidden geometry, which should occur if C4 is broken. And that was done at 8 Kelvin. So, in fact, we have no evidence of broken C4 symmetry.
I just wanted to ask a question. You said there was no coupling to the lattice. How do you do that? Is that a theoretical statement or an experiment?
The statement is because A to G order parameter cannot couple to B1G or B2G in the first order, but it can in the second order. So A to G times B1G times B2G is possible.
It won't couple to the orthorhombic distortion.
It will not couple in the leading order.
Okay, but it could couple
In the higher order.
or in A2G channel to other modes.
There is no A to G form, so there is you can't. A to G is anti-symmetric under XY exchange, so you cannot build a phonon of this symmetry. Right? And you can't in fact build a density. So the only mechanism actually to have this A to G that I now, if I don't need to include spins, is somewhere I had it. high is essentially what I need. I need to have an operator that is antisymmetric on the XY change. For example, a circular current, like one is proposing for high PC would lead to that, or something of this kind. The Raman vertex has to induce, at least in intermediate state, some kind of flux.
Well, if there are no further questions, let's thank Hirsch very much.